Okay, so we have mentioned the word embedding and the word prediction problem, right? In the following pages, we will discuss two concrete methods for starting the word to vector problem or word embedding problem. The first one is called CBOW, and second one is called skillgram. So both of them they can be serving as a method for starting the embedding vectors of the words, and they can also be applied to do the prediction of the words as well. However, they work in different ways. And we will illustrate in detail what are the similarity and also the difference between these two methods. So first of all, let's talk about the CBOW. What is CBOW? CBOW denoting the continuous backward words, right? I'm not sure if you have heard about the backward words or not. Normally, if we treat this document as a set of words, then we can represent it as backward words, right? It will be treated, these words all doesn't matter anymore, and we treat them as backward words or a set of words. So for the backward words, we can predict the current word using the surrounding context. We illustrate with a concrete example. Let's say we have a sentence. The curtains are open and the stars shining in on the something like that, right? So this WT, we denote this one as the current word. Before it and after it, we can define its surrounding context. So for the four words before the WT, we can define them as the surrounding context before the word, and it was similar for the four words after this current word. Right? They all together we define as a context for the WT as shown here. So given a window size C, for example, we can define the C to be 4 for this example shown here, right? Given a window size C, we can represent the context of word WT as the set of words or sequence of words WT minus T until WT plus C, right? So we can define all the words as the context for the current word. So according to the sentence, actually given these words in the context, we can infer the potential probability for the word to be starred or the missing word for the current location. So for the CBOW, this model, we try to predict the current word based on the surrounding context. So the probability to infer the word WT based on the context, based on context we defined before, we can represent it as P probability of WT based on the condition of context, right? Here, if we assume we know the embedding vector for the words already, we assume to be sure, even though this one will be a variable to be learned. If we assume we know the embedding vector for the words, we can denote this WT is embedding vector as a variable V, this vector, right? And we can define the embedding vector for each word, right? And similarly, we can define the variable for all the words in the context, like surrounding the word. So when it comes to the embedding for the context, this as one group, right? We can define this context embedding vector or representation as a summation of all the entries, all the vectors inside the context, right? So therefore, we can represent the context of word WT as what? As a embedding vector as well. It is represented as the average vector of all the words inside the context. Because we mentioned for the context, it covers WT minus C until WT plus C, right? With this WT excluded. Then we can sum all the words representation inside it together to define the vector for the context, it as a group, right? So here we assume we know the V vectors, even though it is variable to be learned. Then according to the vector we define here, we can further infer the potential word, right, based on context. And we can illustrate the way we can do the prediction of this missing word or the current word based on surrounding context. Here given the inputs, which are the words surrounding the current word, and we can sum them together, right? We can sum them together. Also, we can further use it to define or to infer the potential word of the current location. This is outline illustrating the CBOW model architecture. Actually, we can define the mappings we show here by the lines as multilinear perceptual models. So we can illustrate the CBOW model in more detailed information. Before we mention, we assume we know the embedding vectors for the words, even though they are variable to be learned actually. So here we illustrate the learning process for the CBOW model given the input words. We mentioned we assume we know the surrounding context of the current word, right? We can represent them as inputs. Each one can be represented as one hot coding for the words in the vocabulary set. We can represent the words as its corresponding one hot coding, and we can fit them into the model for the CBOW, right? So to learn the embedding of the words in the CBOW, we can represent the mapping as the multilinear perception as shown here. We can define one mapping by the MLP, then we can further integrate all the embedding vectors together by summing them together, right? We showed before, we have one summation here. And we sum them together to define the embedding vectors for the context, right? For for the context. And we can further utilize this context to infer the potential word for the target location, right? By using one more layer to predict out. This will be the prediction of the word we want to infer for the current location. And we also define the mapping as an MLP as one layer as shown here. Also, this output can be normalized by softmax function, right? We can infer the probability for the word to be certain tokens in the vocabulary set. And we can represent this one as the corresponding probability distribution among all the words in the vocabulary set, also compared with a ground truth to define loss function for learning the model, right? So you can see by defining loss function, for the target word, we'll be able to learn the model architecture, right? At the same time, we can also learn the embedding vector for all the words we're serving as the inputs. Because once the model architecture is learned, then we can learn its corresponding embedding vectors by times this W with x1, right? So in this way, we can also learn the embedding vector for all the words inside this vocabulary set. This is the way we can learn the Seibao model. At the same time, we can also learn its corresponding embedding vector for the words in the vocabulary set. You can see for the Seibao model, we are inferring the target words based on the surrounding context. Another way we can do the inferring of the words is to infer the surrounding context by utilizing the missing word instead, which is called skillgram. For the skillgram in this model, we try to predict surrounding context by using the current word. It is in another way, right? So in this page, we show you the architecture for the skillgram model. How do we define the model and how can we learn the embedding vectors for the words inside the vocabulary set. The formula given sentence as well as the window size, we can represent the corresponding context of a word WT as its context, right? It covers both the C word before it and after it. And however, for the skillgram, this method we try to infer the context based on the missing word or based on current word. And we can define the probability to infer the context. This all the words in the context given or based on the condition we know the WT. We can define this one as the probability distribution, right? So to illustrate the learning process of the skillgram, we also draw some sketch on the right hand side, given a WT, and we can utilize this WT to infer the surrounding context, right? The WT minus 2 until WT plus 2. And all the lines we show in architecture denoting some mappings. We can define the mappings as the multi-layer perception in a very simple way, right? And in this way, we can define the skillgram model by utilizing the multi-layer perception in this page as shown here. So given the input here, it will be one single word. However, we can represent this one as a one-hot coding for the input words. And by fitting this one as into this similar like the MLP model, we can learn its embedding vectors, right? Like this one. And furthermore, we can utilize this embedding vector for the input words to infer the surrounding context, right? By defining the y1, y2, yc as shown here. So for this y1, y2, yc as shown here, we have different learning targets. Of course, we can also normalize the prediction results with softmax to get the probability distribution among all the words in the vocabulary set. We can know which one is more likely to be the true words according to the predictions, right? And we can further compare the prediction with the ground truth. We can define loss function for all the words in output. Alright. So it covers the prediction of all the words in the context of the target word actually. And we can define loss function for all of them, then can sum them together to learn to define the object function for learn the model. In this way, we can learn the embedding vectors for all the words in the vocabulary set as well. Because we learn the mappings, then we can, given the one hot coding, we can learn its corresponding embedding vector in a very natural way, right? So you can see this is another way to do the prediction of the words, and we can also learn the embedding of the vectors with the skillgram method as well. So the skillgram and the Seibao method, they work in a very similar way, however in different directions, right? And we'll provide you with the comparison between these two methods. So these two methods can both serving as prediction model for the words as well to learn the embedding vectors for the words as well. They have some common parts. They can both learn the word embeddings based on their surrounding context, or both works well in unsupervised manner, requires no extra supervision information, because we're learning the word embeddings based on the surrounding neighborhood of the words, right, and nearby the target words. So also they have some differences. For the Seibao, we are inferring the target word based on context. However, for the skillgram method, we are inferring the context based on the target word. Even though this difference is very minor, however, in the learning process, these two different architectures actually we need two different performance in some of the cases. For example, for the CBOW, because we are inferring one single output, right? Normally it will be much faster than the skillgram. This one we infer multiple words as output. So CBOW will be much more, several times faster to train than the skillgram method, also slightly better accuracy for the frequent word predictions. As to the skillgram method, it works well for a small amount of training data because we are predicting multiple words at one time. In other words, we can train the model to be more powerful, right, if we have a very small data set for training. Also, it is able to represent very well even for the real world of phrases actually. Okay, so these are the two methods we can utilize to learn the embeddings for the words and in the vocabulary set according to the sentences we have. And we can learn these models or the embedding vectors by inferring some of the words either from the context to the target word or from target word to the context in these two different directions. Okay, they both can work well actually.